Hello. In this video, we're going to continue our exploration of sequences by introducing and investigating a particular notion of the limit of a sequence, which we're going to call convergence. We're going to see some examples of sequences that converge and some that don't, some that diverge, and we'll explore a formal definition of what a limit of a sequence is. So the intuition, the key idea to have in your mind all throughout this video and further in our study of sequences, is that the convergence of a sequence, a possible limit of a sequence, is based on the long run. Where is this sequence going if I keep scrolling to the right along the terms of the sequence? If I look further and further down my list of numbers, are they getting closer to something? And if so, what is that and how do I find it? And if they're not, can I try to explain why? So I picked two examples here, one of them which is getting closer to something in the long run, another one which is not. Let's look at the AN sequence. This is the same AN sequence I was using in the previous video, the 1 over n squared sequence. And notice, just as like we were talking about in the previous video, the sequence goes 1, a quarter, a ninth, a 16th, and so on and so on and so on. And we can see that those values are just getting smaller and smaller and smaller. They're approaching 0. Or in other words, if I plot the first term at the height of 1, and I plot the second term at the height of a quarter, and then the third term at the height of a ninth, and I just keep going like this, then as I scroll to the right, as I go very far down the line in the long run of the sequence, those values are getting closer and closer and closer asymptotically to 0. So I could say that the limit of this sequence is 0. However, let's compare to another sequence that I'm going to call Bn. This is different from the Bn I was using in the previous video, but this sequence is defined as -1 to the n. So when I have an odd input like 1 or the third term or the fifth term, -1 to an odd power outputs -1. Whereas if I plug in an even n, the second power, the fourth power, the sixth power, all of those are going to output a +1. So this sequence just oscillates back and forth, -1, +1, -1, +1. And so if I draw that sequence down here, it looks like this in terms of the list, the terms of the sequence. And then if I make a graph of that like this, I'm going to see, well, the first term is -1, and then the second term is +1, and the next one's -1, the next one's +1, and they're just going to keep jumping back and forth like this. And so in that sense, this sequence doesn't have a limit. It does not approach a specific value. It doesn't get closer and closer. Maybe one way to imagine this is if I'm standing on the x-axis here, if I'm standing at y = 0, I'd have to reach out pretty far to grab a hold of either of the nearby points. They're all distance 1 away, and as the sequence travels further to the right, they ain't getting any closer to me. I still have to keep reaching out very far to pull those, to reach those dots. Whereas in the first sequence, AN, if I'm standing on the x-axis, y = 0, the dots get closer to me. I could just stand there and wait, and then in the long run, those values are just getting closer and closer and closer to me in distance, and I could reach out and eventually touch them as they get closer. That's one way to intuitively think about convergence, the limit of a sequence, is are the numbers approaching a specific number? Are they getting closer and closer to something? So here's that formal definition that we're going to use to talk about convergence, the limit of a sequence. It says a sequence converges to a limit if the terms of the sequence get closer and closer to that number, that limit L, as n, the terms of the sequence, that index n increases. So in other words, if I can make the terms of the sequence as close to L as I could possibly want by looking further and further down the sequence, that's what it means to say that the sequence converges to L. And we'll write it this way. We'll say that the limit of AN is L. Or maybe even another way of saying that is that the limit as n goes to infinity of the sequence AN, that equals L. That looks a lot more like the notation you would have used in a calculus course to talk about the limit of a function. We'll apply the same notation and talk about the limit of a sequence here. So if we can convince ourselves that a sequence converges to something, and it doesn't even matter what number that is, what that limit L is, then we'll say that the sequence is convergent. That means it approaches a specific number. convergent means approaches some specific value. And by contrast, if a sequence doesn't converge, we're going to say it diverges, or it's divergent. And that just means that the sequence fails. It does not. It fails to approach something specific. And so in the previous set of examples on the previous slide, the AN sequence is converging to 0 because the values are getting closer and closer to that 0. If I lay out a number really close to 0, like 1 over 100, well, eventually my terms are going to get within that boundary away from 0. And if I make a closer boundary to 0, I might have to wait longer in the sequence for the terms to get below that line, but they'll eventually get that close to 0. However, in the BN example down below, if I lay out a set of boundaries around 0, let's say, then my values of the sequence don't land within those bars. They stay outside. And so in that sense, this sequence doesn't converge to 0, and it doesn't really converge to anything else either. It's just going to keep jumping back and forth from -1 to +1. It's not approaching something specific. And that's the sense in which it diverges. It fails to go towards a specific number. Here's some facts about convergence and divergence. If you read about this in a calculus textbook, you'll see a theorem about limit laws and blah blah blah, all that. But here are just some intuitive ideas you can keep in mind. If a sequence converges to some limit, it's a specific number. It can't converge to do two different things. It can only have one limiting value, L. And it truly is possible for certain sequences for us to realize that it converges to something, even if we don't know what that number is yet. So try to have that in the side of your mind. Maybe not all the way in the back, but not right in the front either. Have that on the side. It's possible, and we'll see some examples later, where we can explain that the sequence must converge to a limit, even if we aren't confident what that limit's actually going to be. And by the way, if a sequence is unbounded, then it cannot be convergent. Remember I talked about bounded and unbounded at the end of the previous video? If a sequence is unbounded, that means its values are allowed to grow above, outside of a particular, no matter what limit we could possibly set up. So a good example of that, of an unbounded sequence, is something like AN is defined by, let's just make AN equal to n itself. This sequence just grows and grows and grows like that. It doesn't approach a specific number. Another way to say that is the limit of that AN is just growing to infinity. That's divergent. It's not approaching a specific number. It's just going to get bigger and bigger and bigger. And in that sense, I would say it diverges to infinity. That's the conclusion I would reach for the example we're looking at down there. And then here are three so-called limit laws, you could say. If I have two sequences that converge to different limits, then when I add their terms together, those terms approach the sum of their limits. That should make sense. If I have a sequence that converges to a limit, and I multiply all of the terms by a specific constant, then the limit is, the new limit is the old limit times that constant. That should also make sense. And here, this one at the bottom says, if I have a sequence that converges to some limit, and I apply a function to all of the terms of the sequence, then I'm allowed to apply that function to the limit. This is kind of a chain rule, a composition rule for sequences using continuous functions, and we'll see this come up in some examples later. So let's explore some examples of sequences, exploring their terms and asking, are they convergent or divergent? Pause the video now and look at these two and see what you think. Okay, so you might notice that this first example, I would say it converges to 0. I'll lay out the conclusion we're going to get to right away, and then we'll make some observations about it. First of all, let's call this one AN. Here's a way to give an explicit formula for the terms of that sequence. It's essentially 1 over the odds. I know I didn't write it this way, but you could always think of 1 as 1 over 1. And so a 1, a third, a fifth, a seventh, a ninth, those are all 1 over the odd whole numbers. So a way to generate odd whole numbers like that is with the 2n minus 1 pattern. So look at this. If I plug in n equals 1, if I make n the value 1 right there, I get 1 over 2 minus 1. I get 1 over 1, I get the first term. If If I make n 2 right there, I get 1 over 2 times 2 is 4, minus 1 is 3. I would get 1/3. I get the second term in the sequence. I could keep going like that. No matter what n I plug in, I get the nth term correspondingly in the sequence. And then a graph of the sequence would look like this. The first term is 1, the next term is a third, a bit smaller, and then a fifth, smaller than that, then a seventh and the ninth. These are essentially all points along the way of the 1 over x curve that's going to decrease down to 0. So I'll say the limit is 0. It's even decreasing on its way to 0. It's monotone in that sense. What about the second example down at the bottom there? I see a couple things happening. First of all, I notice that it's alternating in sign. I see that it goes plus minus, plus minus. And remember from one of the examples in the previous video, a way to generate that is to have a -1 to an exponent. And in this case, I'm going to have -1 to the n plus 1, because I want, when n equals 1, the first term of the sequence, I want that to be positive. So -1 squared, I want that n equals 1 to output a positive, so then in even power. And when n is 2, I want the second term to be negative, so when n is 2, I get -1 cubed. That's negative, that's good. I'm making that pattern match. And you may also then notice that, again, if I write 1 over 1 that way, then the denominators here go 1, 2, 4, 8, 16. Those are all the powers of 2. So another way to write all of this, the pattern, let's call this Bn. I could say it's given by, defined by, B sub n is -1 to the n plus 1. That introduces the alternating sign. And then in the bottom, I want 2 to the something. I want a power of 2. In this case, I'm just going to be careful in my thinking and say it's 2 to the n minus 1. Why is that? Well, because when n is 1, the first term, I get 2 to the 0 power. 1 is 2 to the 0. And that corresponds to n equals 1. But when n is 2, I want this to output in the denominator 2 to the 1. And when n is 3, I want this to output in the denominator 2 to the power 2, 2 squared, which is 4, and so on. And so that's why I'm seeing the n minus 1 exponent happening from the pattern that I see down here. What is this sequence going to do? Well, I could plot it out like this. The first term outputs a 1. The next thing outputs a -1/2, so closer to 0, but underneath. And then the third term outputs positive 1/4, so a little bit closer to 0, but above. And then it's going to go under, but closer, and then it's going to oscillate back and forth. So I can say it's oscillating, it's not monotone, but it still does converge to 0. Here are some different examples, and again, why don't you pause here and see what you can explore in a couple of minutes, and then check back and we'll compare our ideas. I could start to plot out these terms by looking at the pattern here. It looks like I have a block of 4 that repeats. 0, -1, 0, 1, and then that repeats again. 0, -1, 0, 1, and that's just a repeating block of 4. I'm going to infer that that's the pattern meant by whoever made up this example. Hey, that's me, so I know what I mean. And let's see what that looks like. At the beginning, it outputs a 0. When n is 1, the first term, and then it outputs a -1, and then it outputs a 0, and then it outputs a +1. And then it does the same thing. It's going to go 0, -1, 0, 1, and so on and so on. This is divergent. Notice that it's just going to keep going up and down like that. It's not approaching a specific value. For a sequence to converge to a particular limit, the outputs, the terms, the numbers in the list, in the sequence, they have to just get closer and closer and closer to some limiting value as I move further to the right, as I move along the sequence. And I ain't seeing that here. These numbers are just going to keep oscillating down and then up and then down and then up, and then just going to keep doing that kind of like a sine wave or a cosine wave. And in fact, that's actually something that you may or may not have noticed, but I'll mention it here. There's a way to write out a formula for this pattern. In fact, I could write out this pattern as cosine of n times pi over 2. Okay, now why does that work? Let's just see that first, and then I'll talk about how I came up with that myself. Why does that work? When n is 1, what's cosine of pi over 2? That's asking for the x-coordinate of that point up there at pi over 2 radians, or 90 degrees, and that's 0. So I get the right first term. That's good. And then when n is 2, 2 pi over 2s is pi, or 180 degrees. What's the cosine of that? What's the x-coordinate of that point? It's negative 1. That's the next term in the sequence. 3 pi over 2 is this 270 degree angle down there. What's the x-coordinate of that? It's 0, just like I wanted to see. And then 4 pi over 2, or 2 pi, is all the way back around the circle, and that outputs a 1, the x-coordinate, the cosine. And that's exactly what I see. And then that pattern repeats. So this pattern is based on those 4 angles around the unit circle and their corresponding cosine values, the x-coordinates of the corresponding points. Now, how did I come up with that? Well, you may have noticed the kind of wave pattern coming out of those dots, so I thought to use a sine or a cosine or something like that. And I'll say here that this is not the only way to write down the pattern of the sequence here. There's a way to do it with sine, there's a way to do it differently with cosine. Try to come up with some other ways of doing it. All right, let's look at the Bn example down here. Let's start exploring what the terms of this sequence are. When n is 1, what's 10 to the negative 1? That's 1 over 10, or in decimal form, that's 0.1. So the first term, b1, is 1 minus that, which is going to be 0.9. How about when n is 2? 10 to the negative 2 is 1 over 10 squared. It's 1 over 100. It's 0.01. And so b2 is 1 minus that, and that's 0.99. And then when n is 3, I'll let you do the computation, but you might see where this is going. b3 is 0.999, because it's 1 minus 1 over 1,000. And in general, bn is point a bunch of 9s, and specifically there's n 9s in there. So for example, when n was 2, I saw 0.99. When n was 3, I saw 0.999. And so what I'm going to see is n, exactly that many 9s appearing in the decimal after the decimal point there. And so this limit is 1. I keep tacking on 9s to the end of that. So b sub 100 is 100 9s. That's not exactly 1, but it's really close. And then b sub a million is 0.1,000,000 9s, and that's even closer to 1. And none of them are ever equal to exactly 1, but they're approaching 1. Here's some other examples. Again, pause the video, explore a little bit, see what you can find, and then we'll compare. Here we are. I could write out some of the terms of this an sequence. Let's see, when n is 1, I get 2 plus 1 is 3 over 1. When n is 2, I get 5 over 2. I get 7 over 3. I get 9 over 4. 11 over 5. And you might notice the pattern here where each denominator is a whole number. That's coming from the n. And each numerator is an odd number, because if I take a number and I double it and I add 1, I get an odd number. And so that's why I'm seeing this here, where every time the numerator is the bottom, the denominator, doubled plus 1. What's happening in the long run here? Well, let me ask a corresponding question that you may have seen in a Calculus 1 course. What if I took the limit as x goes to infinity of 2x plus 1 over x? Well, you may notice that the top and the bottom both have a highest power of x. And in the long run, as x becomes a huge number, that plus 1 kind of doesn't do anything. It means diddly squat in the terms of x being a huge number. Like if x is a billion, 2 billion plus 1 is pretty much the same thing as 2 billion. And if I divide all that by 1 billion, I get something pretty close to 2. And so you could kind of convince yourself that this is going to output 2 as a limiting value, and that's what this sequence converges to. So maybe think back to some limits you've done in Calculus 1 before. Something like this is hopefully something you can think through based on your previous work. Now the example down here at the bottom is a little different because it's also something that you've maybe seen before. If I asked you this limit, you may have learned some technique for doing this, but just try to think about what the pattern of the terms here is. So the numerators are all powers of 2 and the bottoms are all squares. So 2 to the 1 is 2, 1 squared is 1. 2 squared is 4, 2 squared is 4. Okay, so that outputs 1. 2 cubed is 8, 3 squared is 9. 2 to the 4th is 16, 4 squared is, oh, that's funny, that's 1 again. 32, the numerators are doubling, the bottom is a square. 64 over 36, 128 over 49, and then eventually, after a certain point, like around here, originally the terms were kind of going up and down a little bit, but after that point, they're all going to grow and grow and grow and grow. The reason for that is doubling the top every time has a much bigger effect than increasing the square very slightly in the bottom. And so one thing that I'll say about this just for now, and I'll come back in the next video when I talk about techniques for this. In the next video, I'll give a specific technique for what we're doing here. It's L'Hopital's rule. But I'll just say for now that the exponential thing in the top, 2 to the n, that's growing to infinity. So is the n squared thing in the bottom. That's also growing to infinity. But the exponential thing is growing to infinity way, way, way faster than the n squared thing. So my conclusion out of all of this would be that this sequence is divergent. It's diverging. I can even be a little more explicit by saying it's diverging to positive infinity. Here's some more examples. Pause here, explore a little bit, see what you find. All right, let's explore some terms by writing some out. N squared over n squared plus 1, so I'll keep squaring a number and making the denominator 1 bigger than it. So 2 squared is 4, so I have 4/5. 3 squared is 9, so I have 9/10. 4 squared is 16, so I have that out of 17. And so on, and so on. Oops, I didn't mean to say that that ends. Keeps going. Now, if you think about it, just using the same kind of thinking I was saying in the previous slide, if I make n a huge number, then n squared is way bigger, and adding 1 to that doesn't do diddly squat. Making a huge number 1 bigger doesn't change it by a lot. If I take a billionaire and I give him $1, or her $1, they don't really notice. So in that sense, the top and the bottom of this fraction are pretty much the same thing, and their ratio is going to get closer and closer to 1, because I have a really big number divided by essentially the same really big number almost. And as n gets even bigger and bigger and bigger, that ratio becomes closer and closer to 1. You can kind of see that happening here. The top and the bottom are both becoming bigger and bigger, and they only differ by 1 every time. And by the way, here's a graph to see that. Here's the function x squared over 1 plus x squared. I just wrote the sequence we're talking about with x's instead of n, so I can graph it here. And there's the horizontal line y equals 1, the limit we're expecting. If I zoom out a little bit, you can see the symmetry of the graph, but we're really interested in what happens as x goes to infinity, the input. So in other words, if I scroll to the right along this graph, and notice that the curve is just going to rise and get really close to 1, and so it looks like it's almost the same. If I zoom in there, I can see that they're slightly different. But as I scroll further to the right, if I move down the long run of the sequence, they get closer and closer. And so eventually they're getting much closer to 1. They're converging to 1. This example down at the bottom I'm using to introduce to you this notation that, even if you haven't seen before, I'll define what it is right now. That is not a very excited n. That is something that I would read out loud as n factorial. And it means multiply all the counting, the whole numbers, from 1 up to n. So for example, 3 factorial means 1 times 2 times 3. In this case, that's 6. 4 factorial is 1 times 2 times 3 times 4. That's 24. As another example, 5 factorial, that would be 1 times 2 times 3 times 4 times 5. Or, hey, another way to see that is that's exactly 4 factorial. The 1, 2, 3, 4 multiplied together. So that's 24 times 5. That's 120. And real quick, I've just jumped over to the very first video for this class where I said I'm going to motivate infinite sequences in series. Remember I said let's graph the sine function along with some polynomials, and I said don't worry about where these numbers are coming from. Well, here's a little preview. The 3 factorial was 6 that we just talked about. Look at that 6 there. 5 factorial is 120. Look at that. The cube goes with the 6, the 3 factorial. The 5th power goes with the 5 factorial. Believe it or not, 7 factorial, that's what the 5,760 number is. So I just want to mention that tie into what we were doing earlier. Here, that allows me to say what the terms of this sequence are doing. The numerator, the top, the -1 to the n, that's going to make the sign oscillate. Negative, positive, just like we've been seeing in a few examples. When n is 1, I get a -1 to the 1, so negative. So I get -1 over 1 factorial, or just 1. Then I get +1 over 2 factorial, -1 over 3 factorial, +1 over 4 factorial, -1 over 5 factorial, and so on and so on. And these numbers are going to oscillate around and eventually converge towards 0. Just like the oscillating sine sequence that we worked with in the last video, Bn, that was jumping up and down around 0, this is also converging to 0 in a similar sense. The denominator gets bigger and bigger and bigger. The numerator is always positive -1, so that ratio is going to be getting smaller and smaller to 0. Here's one more example because I just wanted to remind you that we don't always have formulas for the terms of the sequence like we've been seeing in all of these so far. In some cases, we might have something defined recursively, like this. So this is a recursively defined sequence in the sense that I'm giving you the first term in the sequence, g1 is 16, and then thereafter, each term is the square root of the one before it. So in other words, g sub 2 says it's the square root of g sub 2 minus 1, or g1. So g2 is the square root of g1. So once I know that the first term is 16, the next one is 4. And then the next one is 2, because root 16 is 4. And then root 4 is 2. And then root 2 is, well, that's a number. It's like 1.41 something. And then after that, I'm going to have the square root of the square root of 2. And then, oh boy, this becomes hard to write. I have just a bunch of nested square roots. So the question is, what's happening with that? Maybe we should do some calculations. So here I've pulled up a calculator, and I've just put in the first term 16, because I can start applying the square root of that. And I can see that that's 4. And then maybe I'd want to take the square root of the term that I just got, and I get 2. And then maybe I'd want to take the square root of the term I just got, and that's where the 1.414 is going to come from. And then if I take the square root of, I'm clicking on that number just to use what's stored there, I get 1.189. And then if I say what's the square root of that, I get something a little smaller but still closer to 1. And there I've started to write those approximating numbers on my list, my sequence of terms. And it turns out if you keep doing that, this approaches closer and closer to 1. 1 is kind of a fixed value where if I take the square root of it itself, I get itself as an output. And that's what's happening. These numbers are just going to get smaller and smaller down to 1. Taking the square root of a number bigger than 1 makes it a tiny bit smaller, and they're going to get closer and closer to this fixed value of 1.